In the next section of the course, we're going to focus on a type of motion that we've ignored up to this point, but is actually very important for a lot of practical applications of motion, and that's rotational motion. I mean, think about it. We've got machines with gears and wheels. We ride our bike, the wheel rolls. If you throw a ball, it spins in the air. Lots of things rotate, and it's an important type of motion that we have to discuss. What we'll consider is the rotation of what's called a rigid body. A rigid body is one where we envision that the pieces of the object, whether you think of these as the atoms or the individual nuts and bolts of the machine, the pieces of the object maintain a constant distance to one another. So if I draw a line segment connecting any two pieces on the object, that line segment has constant distance. That's the definition of a rigid body. All pieces of the body have a constant distance between them. Now that doesn't mean that all different pieces of the body have the same distance between them as all the other pieces. That would be a weird object. But it means that as the object moves, the distance relationship between its parts doesn't change. Let's look at a rigid body and see what this actually looks like. So here's a calculator. It's pretty rigid. If I look between this yellow button and this red button, they're a certain distance apart, maybe about 5 or 6 centimeters. And no matter how I move this object around, twist it, spin it, rotate it, slide it up and down, left and right, the distance between these two buttons is always the same. And the distance between any two other buttons is always the same. That's what makes this calculator a rigid body. If I were to take this calculator and squash it or crush it or twist it and basically destroy it, I would change those distance relationships and it would cease to become a rigid object. Now, no real object is perfectly rigid, but it's a very good approximation for solid objects that are made of metal, wood, bolted together, basically pieces of machines and technological applications. So a rigid object can still move, but its type of motion is very restricted. There's basically two ways that it can move. The first way a rigid body can move is called translation. This is the technical name for the type of motion we've been discussing all along in the class. You know, we have a block of wood, we've got a cart with wheels. All of the pieces of that object move with the same velocity. So we can tell that if all of the pieces moved in the same direction at the same speed, then they would all stay the same distance from each other. So a translation maintains the rigidity of the object. So all pieces have the same velocity in a pure translational motion. The only other way that a rigid body can move is by rotation. And in rotation, what we mean is that overall the body doesn't have any motion side to side, up and down or anything. Its center stays at the same location, or there's some point on the object that stays at the same coordinates. But the object spins and rotates around that point. So a simple rotation would be something like this. We've got a center, an axis of rotation that's in the middle of this calculator, and it just spins end over end, not moving overall to the left, right, up, or down, but definitely changing the location of its pieces. So when we do a rotation, the requirement for the object to remain rigid is that all the pieces of the object need to rotate by the same angle. So if I take my object again and I rotate it by 90 degrees, all of the pieces rotate by 90 degrees around some central point. A direct corollary to this is if the rotation happens over time, then in a given interval of time, all the pieces must rotate by the same angle in that interval of time. And that applies to any interval of time. So, in addition to this, exactly the same fact said in a different way is that all pieces must have the same axis of rotation and the same rate of rotation. Okay, so that's the two types of motion that a rigid body can execute. Now let's introduce some variables that we use to describe these. If we have a translational motion, now, to distinguish a purely translational motion from motion of the pieces that might result from a rotation, we'll call the translational velocity v with a subscript cm. This comes from the center of mass concept that we briefly heard about in collisions. But it's basically describing, here's the center of the object, the average position of the object, that's moving all together. So the translational velocity we'll now specify as vcm. To specify the rate of rotation, we'll use a quantity called the angular velocity. The symbol for angular velocity is a lowercase Greek omega, not a w. We've actually seen this symbol before. We used it when we discussed objects going in circular trajectories, a uniform circular motion. We would have a certain angle covered per unit time for that object's position vector. This is similar, but it's a little bit different in concept because now we don't just have one object going around in the circle. We have an entire object that's continuous, that has matter everywhere, and it's all rotating together. So with these two types of motion possible, the individual pieces of the object will move in certain ways. So let's draw a diagram of an object that's rotating. We'll put the axis of rotation at the center, and we'll define our angular velocity to be positive for counterclockwise rotations and negative for clockwise rotations. So this shows an omega angular velocity that's greater than 0 with the arrow pointing this direction. This matches our convention for angle measurement as well. Now, this is not just a single object or an imaginary circle. This is like a whole solid object. It's got pieces of matter everywhere within it. So let's think about how is a given piece of the object going to move? Well, in the case of translation, it's very simple. All the pieces acquire the same velocity. So let's put that off for the moment and focus on the new thing, which is how would a piece move when the object is only rotating with angular velocity omega? Well, we've already worked this out somewhat too, back when we did uniform circular motion. If we consider each piece of the object to be its own thing, then each piece would go on a circular trajectory around the axis of rotation, and the magnitude of the velocity that that piece travels at would be equal to omega, the rate of rotation, multiplied by the distance to the axis of rotation for that piece. If we looked at, say, a different piece of the object down here, we'll call this first one V1 and R1. This different piece of the object, somewhere in the middle, would have a different distance from the axis of rotation, and therefore would have a different velocity vector. The magnitude of the velocity vector would be smaller if the distance to the axis was smaller. All these pieces have the same angular velocity, though. So these velocities will be of different magnitudes for different pieces, but they'll also be in different directions. Notice that when an object rotates, each piece moves along a circular trajectory. So its instantaneous velocity is always in a direction that's tangential to that circle. So at location 1, this piece is moving in a direction that's perpendicular or tangential to the radius 1 vector. From the axis to its location is a position vector, r1, and v1 is perpendicular to that. For object 2, its position vector points downwards, and so its motion is in a direction that's perpendicular to that position vector. So v2 is tangential to a circle that goes through R2. So these different pieces are all moving at different speeds, and they're all moving in different directions. That's how they're moving. Now let's ask about how they're accelerating. I'm going to make a new drawing here to have a little bit more room. Let's just look at this piece 1 again. And this time we'll just focus on its acceleration. So we've already solved part of this problem, again, when we talked about uniform circular motion. If an object travels in a circular trajectory, it necessarily has to accelerate towards the center of the circle. This type of acceleration is required because the direction of the velocity vector is changing. So we used A sub c to represent what we call the centripetal acceleration. And the centripetal acceleration only depended on how quickly the object was moving around in that circle. So the magnitude of AC was v squared over r. We could equivalently calculate this by the angular velocity squared times r. And the direction of AC, not its magnitude, its direction, was towards the center. So that's one type of acceleration, one component of acceleration that all objects, all pieces of the rotating object must have. In fact, it can occur that if an object rotates too greatly, the material stresses cannot provide this acceleration, and it might actually fly apart. But now when we consider rotational motion in general, we want to allow for the possibility that the rotation rate might change. Not just uniformly spinning constantly forever, but taking a wheel and speeding it up over time, or putting on the brakes and slowing down that wheel over time. So in the cases where the rotation rate can change, we can also have a different component of acceleration in the tangential direction. So we label this as a sub t, and we call it the tangential acceleration. And the magnitude of the tangential acceleration is not set in stone, right? The object could be changing its rotation rate in an arbitrary way. So we can't relate this acceleration in a simple way to the radius and velocity vectors. It's its own thing. What we do know about the tangential acceleration is that is in a tangential direction. So AT is perpendicular to the position vector that goes from the axis to that piece. Okay, so there's these two types of acceleration now for an object that rotates and also might change its rotation rate at the same time. So let's write these out up here. We have a c is equal to omega squared times r, and that points towards the center of the circle, so we use a directional unit hat vector of minus r hat. That's a vector of length 1, so it just gives us a direction that points towards the center of the circle. This tangential acceleration vector, we write this as a quantity alpha, which is called the angular acceleration, multiplied by the position, the magnitude, the distance to the origin, multiplied by a tangential unit vector, theta hat. Theta hat points in the direction of increasing angle, or it always points tangentially to the circle at a given position. So how can we understand why we would write the tangential acceleration in terms of an angular acceleration multiplied by a radius vector? Well, if we want to do that, if we want to justify that, we will need to go to the component forms of these quantities, and it's sort of a proof, but let's go through it here quickly. So this is the position vector of a piece. The angle theta might depend on time in an arbitrary way, but the radius r is constant. We can get the velocity of a piece by just taking the derivative of this. So the r is going to be constant. So we'll get negative r sine theta. And then the chain rule gives us the d theta dt. And in the second, in the y component, we get r cosine theta from the trig rule, and then d theta dt from the chain rule. So our velocity vector is minus r omega sine theta for x, and r omega cosine theta for y. So we use the definition of angular velocity, omega, being equal to the time rate of change of the angle, theta. Second step of the proof is to take the derivative of this velocity vector one more time. But now we have to realize that theta is in here. It's still an arbitrary function of time. And now the angular velocity, omega, is in there as well. And it's also an arbitrary function of time. So when we do these derivatives, we have to do a product rule as well as a chain rule. So the first term is going to be minus r d omega dt times sine of theta for the product rule on x. And then for the second term, we will have minus r omega cosine theta d theta dt. So those are the two x component contributions. Let's do the y component. It will be r d omega dt sine theta plus I'm going to do the second term is derivative of cosine. So minus r omega sine theta d theta dt. So that's the acceleration vector done by derivative. And let's just simplify this a little bit, write it a little bit larger. So there's one contribution here which is proportional to the rate of change of omega. Let's separate those. Let's separate those out. Excuse me. This should be cosine because that was cosine there. I took the derivative on omega. So let's separate these out then into the pieces that are proportional to this derivative of omega. So the first two have minus sine theta and positive cosine theta. That's the first contributions to x and y. And then for the second portion, it will be r times omega squared. So there's an r, an omega, and the d theta dt, that's also omega, so we get omega squared. And then we've got a minus cosine theta minus sine theta. Okay? So that's our acceleration expression by doing derivatives. This vector here is the minus r hat direction. It's the opposite of the radial direction. And this vector components here is our theta hat. That's a vector that has length 1 that's always tangential to the circle at the angle theta. All right, so what we get here is the acceleration is r times the time derivative of the angular velocity times in a tangential direction plus, or let's say really it's, plus r omega squared times minus r hat. So this is what we get for the full form of the acceleration. And then we notice that this part is the centripetal acceleration. That's actually matching the result that we got for uniform circular motion when we ignored the possibility of the rate of rotation changing with uniform circular motion. And this part here is the new one. This is our tangential acceleration. And we notice this is proportional to the distance from the axle. It's in the tangential direction, and it's proportional to the rate of change of the angular velocity. So it makes sense then to define this rate of change of angular velocity as the angular acceleration. And that's what we wrote up here originally. So this is now justified by doing these derivatives and proving it. Okay, so we now have a more or less complete description of how objects move rotationally. We've got some axle, some specific piece of the object, the velocity of that piece of the object is equal to r times omega in this tangential direction. And the acceleration is equal to the centripetal portion plus the tangential portion. our angular measurements now have defining relationships between them. The angular velocity is the time derivative of the angle, the rotation angle, and the angular acceleration is the time derivative of the angular velocity. So what does it mean for an object to have an angular acceleration? It means that its rotation rate is changing over time. It's speeding up its rotation or slowing down its rotation. This gives us the ability to now tackle a number of situations where an object, say, is rotating and begins to speed up, slow down, or is at rest and due to imparted forces, the object begins to rotate. So most of those, a large number of those situations can be modeled as having a constant angular acceleration. So let's write out some special case equations here. These are fully general, but if we have a special situation where we can justify a constant angular acceleration, then we can derive from these the following equations of motion. After an elapsed time t, the angular velocity will change from its initial value to its initial value plus the angular acceleration times t. So omega equals omega 0 plus alpha t. After an elapsed time of t, the rotation angle of an object will change from its initial value to a final value that depends on the initial rotation rate, but then an additional change in angle due to the increasing rotation rate, so 1/2 alpha times t squared. Now you might look at these and say, hey, aren't those exactly the same as the uniform acceleration equations from chapter 2, just with different letters? And yes, you'd be totally correct, because the only difference is really the letters we're using, right? The relationships here that we get these from, the defining equations, are exactly of the same form. The only difference is now we're measuring angles per second, and angles per second, instead of distance per second, and distance per second. So the equations all have the same look of them, with just the angular quantities replacing the linear ones. There's two more shortcut equations we can get from this. If we are wanting to eliminate time as a variable, we can solve the first equation for t and eliminate time in the second equation. And what that will give us is this shortcut equation, where a change in the square of the angular velocity becomes related to the acceleration and the change in angle. So this also has a counterpart for translational motion. Here's what it looks like for angular variables. And the other shortcut equation here is if we say we want to eliminate the acceleration as a variable and get that rid of in the equations, we can solve the first equation for alpha and use that to eliminate the alpha over here. And then what we'll get is theta minus theta 0. The change in angle is equal to the average of the initial and final velocities. So omega plus omega 0 divided by 2, that average value multiplied by the elapsed time. So this is really just showing us change in angle is equal to average angular velocity multiplied by time. We can prove that from these two up here. So these are four equations that we can use then for rotational motions that happen under the assumption of constant angular acceleration.